points is another point where you'll never find the particle. But the larger n gets, the more densely spaced these points get. And you approach equal probability everywhere, which is the classical result. Isn't that interesting? As n gets very large, quantum mechanics gives, the results of quantum mechanics approach those of classical mechanics, classical physics. This is in fact a principle of quantum mechanics. I'll write it down. It's called the correspondence principle. And I'll put it this way, as the quantum number, I'm going to write Qn for quantum number. Okay. Now in higher dimensionality, there's more than one quantum number, so I'll put S in parentheses for quantum numbers. As the quantum number or numbers approach infinity, the results of quantum mechanics just Qm for quantum mechanics approach those of classical physics. So, and that's this correspondence principle we'll come back to. This is something to sort of put in your mind. So that's all I wanted to say about this worksheet. Yes?
As n gets larger, doesn't that just relate to the energy of the particular particle? As n is related to energy.
So it's absolutely true that as n gets larger, the energy is getting larger. So a corollary here would seem to be that as the energy gets very large, then the results of quantum mechanics approach those of physics. Is that what you're getting at?
Yeah, so my question would then be, why does the energy getting larger, why does the energy getting larger relate to classical?
Well, you have to think of the results for quantum mechanics and classical physics, both for very large energies. Okay. But it's the quantum number thing that is really to remember, but you're absolutely right about that correlation. Okay. Any other questions about this? Okay. So we've got a whole bunch of differences, but also similarities between classical physics and quantum mechanics in certain. So I'll put that aside.
Wait,
Oh, go ahead.
now, I have a comment. I don't know if there's like a right way to approach it, but you said like a while ago that like quantum mechanics is more like a discrete, like simple, like idea, and while classical physics is more of a continuous. So like in this, I just kind of like saw it as like, well, if n started approaching infinity, and we previously defined n as being a discrete number, as it just went to infinity, it became more of a continuous number, meaning that like it just kind of transferred on to like more of like the classical field, since like it started following like the rules of classical physics and transcending from quantum.
Yeah. So there's a lot of truth in that. It's not perfect, but there's a lot of truth in that. And the energy levels of a particle in a box get farther and farther apart as the energy gets large. So you have to just be a little careful. But in general, that's true. Okay. Now, we also had the degeneracy worksheet, but I think I want to put that off till later in the day, and we can break up topics that way. But I need a volunteer to remind me to actually get to the degeneracy worksheet at some point. Do I have a volunteer? Somebody's going to remind me? Okay, Steve, thanks. So if I haven't gotten to it by, say, 12:45, remind me. I might not stop that moment, but then I'll stop short. Okay, thank you. Cool. So with that, I want to introduce a new topic, a new model problem. You'll find slides on this, but for the most part, I prefer to work from the board. It seems dark in here. Am I missing something? Where would the,
It's these slides.
the last one? That did something. This here? I just put my glasses on so I don't. Well, that's on. Something's on now. Whatever it is. Boop, 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 boop. Oops. That was bad. I wish they had these labeled. Okay, I'm gonna go forward with this. I think I'm gonna have this. Oh, come off. Okay. So we're gonna talk about quantum mechanical tunneling. And let me set the problem up with a classical analogy. So we're really in one dimension now. So the classical analogy is this. That can be our x coordinate. Now suppose that there is a hill and you're traveling toward the hill. Now I'm going to let the vertical coordinate be energy. V is, usually we use V for potential energy. So you can think of this mountain or hill as potential energy. But anyway, suppose you're traveling in a car, it doesn't matter what it is. I'm not going to try to draw a car. I mean, I tried to draw a cat and that was a bad idea. So here's the car. Now if you have just a little bit of energy, going kind of slowly, you know what's going to happen. You're going to start to go up the hill, and then you're going to turn around and you're going to go back down the hill. Because you didn't, I mean, I suppose you have to think of, you accelerated, but then you clicked to neutral, so there's no more energy going in. You go part way up the hill, and you just come back down the hill. Now, if we're in 1D, what's really happening is if you have insufficient energy to surmount the hill, you're going to go forwards, and then you'll be reflected. That's what's going to happen in 1D. And this is if your energy is less than the potential energy of the top of the hill. Call that zero, you know. On the other hand, if you've got a lot of energy, you're going to go up and over the hill and on, right? But in one dimension, what we would say is if we're up here where the energy is greater than V naught, I'll go toward the hill. I'll slow down, but I'll keep going and I'll just continue. Would say in quantum mechanical terms, here we're reflected, here we're transmitted. Okay. That's the classical analogy. And it's black and white. Less energy than this, you're reflected. More energy than that, and you're transmitted. You just go over the hill. So, let's see what happens quantum mechanically. Yes?
Sorry, could you go over that again on where it's being reflected and where it's being transmitted, please?
Okay. I'm combining a lot of ideas. Some work visually, some do not. First, if we have the car analogy, I have to be at least in 2D because I'm going forwards and up and over. And I kind of drew it that way. You've too little energy, you go up and you roll back, and more energy, you go up and over. That's the 2D analogy. Now I'm going to bring us back to 1D, okay, and say, well, suppose it's 1D, you're really restricted to this axis. But I pushed my lines up here so that I could have the one direction be at the level of the energy. Now here the energy of my particle is less than the potential energy of the top of the hill. So when I encounter the hill, I get reflected back on it because I can't go over it. Or I can't go beyond it. That's what I'm saying. Up here, we have energy greater than the potential energy at the top of the hill. I'm really restricted to one dimension, but I just keep going. Okay. it's hard to get the point across without going to what's technically 2 dimensions, but the whole issue is really 1-dimensional here.
Can you slow down?
Can I slow down?
Does it slow down the particle?
Yeah, it would. The kinetic energy will diminish as you go in this direction because part of it's being converted to potential. So let me draw another picture that we're going to use a little simplified for quantum mechanics. Okay, so again, we got that. This is the x direction. Instead of having that mountain, I'm just going to have a barrier. And let me make the barrier wider. So we'll let the left-hand side of the barrier be at x equals 0, and the right-hand side be at x equal w. So w stands for width of the barrier instead of L, width. Doesn't really matter, but I think your text used that. Now, vertically, again, this will be potential energy, and we're going to let the top of the barrier be at a potential energy of, we'll just call it V0, some constant. Notice that instead of having a rounded mountain, I've got a square thing. It just makes it easier to do the math on. The essential problem is here, but it's a simpler shape, that's all. Okay. And so that's fine. Now we're going to consider what happens if a particle, now this particle is free to go in this direction as far as possible. Actually, we're going to say it originates at x equals -infinity and travels forwards. And it obviously originated at the beginning of time, which is about 13.6 billion years ago, right? A long time ago. But eventually, and today, it's now coming in and it's going to encounter the barrier. And the question is, what will happen? So we got some particle coming along. It's really confined to the x-axis, as we said. But it's hard to visualize everything. So I'm going to raise it up and let that be the baseline, and the baseline will be at the energy of the particle. Okay, I have to mix things up that way. And the question is, what's going to happen? Okay. Now, we can imagine 3 possibilities, right? We're going to call this, step back. In my initial description here, I'm thinking about time. 13.6 billion years ago, now, okay, time's in the picture. When we go to quantum mechanics, we're going to solve the time-independent problem. But it's easier to think in terms of time to start with. So the particle comes from the left, and we call this the incident particle. Or because the particle is really a wavicle, you can say the incident wave. IN for incident. That just means where it's coming from. 2 things can happen now in principle. It can be reflected. Ideally, this arrow would be at the same energy level as the top arrow, but I have to lower it so that you can see it. R for reflected. Now you're going to say, look, I look at that, I know that those are the only 2 possibilities. Well, I incidentally get bounced off. But we're going to let quantum mechanics deal with the possibility that maybe it actually manages to go through. And if it does manage to go through, we have T, a transmitted wave. T for transmitted. Now I'm going to give the game away and tell you, in fact, there is going to be a possibility of transmission, really a probability. Classically forbidden, quantum mechanically, it's going to be there. Sounds weird, but it's true. So to make sense of this, think it through, we're going to solve Schrödinger's equation. Okay. We're not going to do all the work of solving it, but we're going to set it up and see what we learn. So I'm going to divide space into 3 regions. Region, let's see, let's use a different color. Region 1 with red is anywhere from negative infinity all the way up to here. That's all region 1. Region 2 then is within the barrier region. And then region 3 is just the rest all the way up to infinity. So let's think about this. We're going to talk about 3 different wave functions. One for region 1, one for region 2, one for region 3. And we're going to think about what the Schrödinger equation is in each region. And then the total solution has to match up all these wave functions. So, region 1, Schrödinger's equation is just this, right? In region 1, there is no potential energy, so V is equal to 0, so we just get this. Okay. We actually already know the solution to this, at least the general solution. Can anybody tell me what it is?
Sine and phi.
It would be a sine function if this were an enclosed particle that was restricted to being only in a finite region of space. This is infinite. Yes, there's a barrier here, but it goes all the way to negative infinity. So this is more like the free particle. Yes. So the wave function in this region is going to be e to the ikx, where a is the coefficient. That describes the incident wave, but in region 1 we also have the reflected wave. Remember, I'm now going from the time-dependent situation to the time-independent. So I have to think of sort of the time average of everything. So we have the possibility of moving this direction and also this direction at different points in time. So there's also this. E to the minus ikx describes motion in that direction, some coefficient. Now what is k? So let's think about that. So let's focus just on this part. So suppose let's evaluate what this is. Okay, I'm just focusing on this port. And maybe you'll be happier if I put the A in front as well, although we don't really need it. So let's evaluate that. That's going to give us negative times, we're going to get ik once for the first derivative and then ik again for the second derivative. So we get I squared k squared. I squared is negative 1. That's what we get. And then we've still got the a e to the I kx, right? This is just our wave function. This is just our wave function. This is therefore equal to the energy, because the whole thing has to be equal to E psi 1. Right? So that's the energy. So we have that energy is equal to h bar squared k squared over 2a. Or let's solve for k in terms of energy. So I'm going to write that down here. So that was for psi 1, right? So we got an equation for psi 1, and we have what k is equal to. And notice mass is a given, h bar is a constant, and the energy is whatever energy you've decided to consider. Okay, so that's that. Questions so far? Yeah.
How come there's the negative I term for the left, with the wave function,
Here?
for the solution?
Here? What?
Right to the left. Yeah, because how you said that it was only going one direction.
Oh, but so couple things. First, this is not direct answer to your question. I only plugged in this part of the wave function to see the eigenvalue, but if I had plugged in this part, I would have gotten the same eigenvalue. So I didn't want to take so much time. If you plug in the whole thing, you're going to get the same eigenvalue. Now, in this region, we have both the incident wave. Now to your question, in this region 1, we have both the incident wave and the reflected wave. This is the incident part, and this is the reflected part. Remember, we're now sort of averaging overall time or taking time out of the picture. Both are there. Okay, so that is region 1. What about region 2? No, I'm going to go to region 3 first. Okay, we'll come back to region 2. So in region, I'm going to need more room probably. Go down here for region 3. If we've considered region 1, we're kind of already have region 3. Notice region 3 is also infinite in dimension, in size, right? So it's again, and notice the potential energy is 0 in region 3. Again, we have a free particle. But it's even simpler because this time the particle is only traveling to the right. There's no reflection. It has to reach positive infinity. It's never reflected. There's no wall to. So we don't have that part. We only have this part. Okay, that's all we have. That's for motion in the direction to the right. And E is just some coefficient. Now the Schrodinger equation, notice in region 3 is the same as the Schrodinger equation in region 1 because there's no potential energy. Okay. And therefore K has the same definition here as it does here. So for K, I'll say K equals as in region 1. It's the same K. Any questions so far? What about region 2? And let's just keep things separate here. So that was region 1. So in region 2, we have a different Schrodinger equation because potential energy is non-zero. So we have so that makes things a little different, right? But I constructed this to be a very simple problem. And notice V naught is a constant. It doesn't change. It's not a function of x. It's just a constant within this region, x equals 0 to w. So I'm going to subtract V naught psi from both sides of the equation. I ran out of room, so I'm going to put the psi over here. So notice that this has the same form as this equation. So, hey, I'm going to be able to, the solution is going to look very similar. So I'm going to propose to you Now, this is not a K, this is the Greek kappa. We have to keep it distinct from K up there. So let's figure out what kappa would be. And to figure it out, let's begin by just using this function right here. I'm not even going to bother with the C because it's just a constant. And plug it into the equation. So I'll just go, I guess, right here for now. Maybe I'll keep the C just to make it comfortable. So I need to take the second derivative of this, and just as before, we'll get 2 factors of kappa, and then we're going to keep our C, and we'll get back to E to the kappa x. Looks very much like what we had before. This is just psi 2. And this is now equal not to E, but to E minus V naught, right, because of this. So what we've said is that kappa is that and you might be troubled by the negative sign. And why is there no I, right? E minus V naught, is that a positive number or a negative number? I am considering an energy that is smaller than V naught. I'm considering a particle whose energy is insufficient to get past this barrier classically. E is less than V naught. So this is actually less than 0 for the situation I constructed. Let's multiply both sides by -1 then. This, V minus E naught now is greater than 0. So if we solve, now we can solve for kappa, of course. So notice a couple things. We've got a square root here of a positive number. So there's no I involved. Kappa is real. Well, so is K. K is also real. That's one thing to notice. And notice that we didn't need an I in the numerator here. Everything is real in this region. And the other thing I notice is that kappa and K have very similar forms, except for kappa, instead of E, we have V naught minus E. I'm calling it V naught, not E naught. I'm getting confused here. V naught minus E. That's right. So let's write down our definition of kappa. Here. Okay. Curious thing. Now, so far it's just a bunch of math. You know, what is it? Does it really add up? And what's it going to imply? I think these are the questions. Yeah. So at this point, we have a definition for psi. It is this combination. You have to imagine pasting together psi 1 for this region, psi 2 for this region, and psi 3 for this region. And then we have our complete psi. Perfectly well defined. Now notice that we have coefficients that are not yet determined, capital A, B, C, D, E. So I would say in math lingo that this is the general solution. We don't have A, B, C, D, and E defined yet. So I would say this is the general solution. Did I introduce the term particular solution when we talked about the particle in a box? I forgot to introduce terminology. Do you remember when we, if I go back to particle in a box right here, I said, okay, the general solution what did I say, AX? Whoops. But then I showed that when we introduced the boundary conditions of psi is 0 at x is 0 and psi is 0 at x is L, okay, that led to the coefficient of sine had to be 0 and A itself had to be equal to n pi over L, where n was an integer. And that led to the solution psi depends on n. Once we also normalized we have a name for this solution, a general name. We call it the particular solution. So general solution. So often when we're solving, boundary condition problems, differential equations, we first construct a general solution where we don't take into account our boundary conditions. Then we apply the boundary conditions and we simplify this. That helps define the constants, and we get what's called the particular solution, particular to this situation. I forgot to introduce that lingo. It's something worth learning. Questions? So now we've got a general solution. It's very complicated. 3 parts of psi and match them up. What about the general solution? Yes, Steve?
Oh, just time warning, 12:45, 12:46 actually.
Is it 12:45 already? Holy moly. Okay. Thank you very much. If it gets to 12, stop me, okay? Again, because I do want to do that. So now we've got our general solution here. How do we figure out the particular solution? Any guesses? Boundary conditions? Exactly right. Now quantum mechanics has constraints on the wave function, okay? Now to make this clear, let's see, so what are our boundary conditions? So notice we've got one wave function over here, psi 1, another wave function here, psi 2. At x equals 0, psi 1 must equal psi 2. Well, that's good enough. Well, that has a consequence. What's the value of this exponential of x is 0?
1.
E to the 0, so it's 1. Same for this. So at x equals 0, psi 1 just becomes a plus b. So this means a plus b for psi 1 must be equal to, now what happens if we substitute x is 0 here? E to the 0, 1. So a plus b equals c plus d. Now, at x equals w, psi 2 has to equal psi 3. So plugging in, this means that A, I, K, whoops. a e to the ikx of w that's psi 2 must be equal to psi, oh, I'm sorry, this is psi, I got this wrong. Psi 2 is c e to the kappa w plus d e to the minus kappa w equals psi 3 at w e to the I k w, right? We got two equations in 5 unknowns. That's not enough, right? If we have 5 equations, we can solve for 5 unknowns. General principle, except under strange, unusual circumstances. We have more boundary conditions though. Your wave function must be square integrable, and it must be continuous. This is the continuous part. What else must it be? Smooth? Anybody remember smooth? Smooth? Smooth means the first derivatives must be continuous. So we also have that so the first derivatives have to be 0 at x equals 0. I'm sorry, these two first derivatives. And then we also have at x equals w. You could write those equations out. You're even asked to on the worksheet. I'm not going to write them out. Just imagine we have 2 more equations, one from each of these. So we're going to have 4 equal equations in 5 unknowns. Can we solve for A, B, C, and D? Bad news, no. Good news, we're close. Now you might think, oh, I know there's one other condition. It's got to be normalized, right? That would give us another equation. Wouldn't that be great? 5 equations, 5 unknowns. Bad news. Can you normalize the free particle wave function? And these are kind of free particle-like, right? Can't get them. There is a silver lining. So we do have this unnormalizable, oh darn. Darn. The silver lining is this. For my purposes of teaching you about quantum mechanics, I don't actually need to know those coefficients. What I do need to know, what I'm really interested in, is what is the probability of transmission? Classical physics says 0. What does quantum mechanics say? Quantum mechanics says the transmission probability and we're going to use a T for that. Unfortunately, we use T for transmitted wave here, but now we're using T for transmission probability. It's going to be the square modulus of E. Remember, that's the coefficient of the transmitted wave, E, divided by the square modulus of A. Remember that A is the coefficient of the incident wave from the left, moving to the right. So if everything got through completely, from here, nothing was reflected, everything got through, then the square modulus of A would be equal to the square modulus of E, of E. If nothing got through, then the square modulus of E would be 0. E would be 0, in other words. But if something got through, this is a number between 0 and 1. And it turns out that's what it is. And we can solve for this, we can actually solve for this ratio, even though we can't solve for E and A individually, we can solve for this ratio. I simply ask you to believe that. And I'll show you what you get. You can look this up in your textbook. Okay. This is just an equation to look at. You can't really see where it came from. And I'll double check it because I don't want to make a mistake. Yeah, that's right. Now, a couple things about this. Remember the definition of kappa is right here. Notice as the difference, three things I want you to notice. Notice that as mass gets large, kappa gets large. Notice as V naught minus E gets large, kappa gets large. So kappa is large if the mass is large or if the barrier is very high compared to the incident energy. And then the W here is the width. Okay. Now, this equation is easier to think about if you simplify it for large, high barriers. So if kappa W is much greater than 1, this simplifies, and that covers most of our situations. So let's just write down the simplified thing. Notice if kappa W is larger than 1, this negative, if it's very large, then e to the minus large number is negligible compared to this. So I can kind of ignore that. And this 1 will become very small compared to this. Okay? And so this becomes right, this is to the negative 1, so this becomes on top. And now we have that's T. This is easier for thinking about qualitatively. I need to tell you what epsilon is defined as, by the way. We define epsilon as the ratio of E to V naught. Okay. So as long as E is much less than V naught, epsilon's a small number. Okay. Notice when epsilon equals V naught, then we have, when E equals V naught, epsilon becomes 1. This appears to equal 0 all of a sudden. Anyway. Just make sure. Yeah, that's right. Okay. So notice a couple things. Notice the negative sign here. So if kappa is large, that means that if the mass is very large, kappa will be large. This is e to a minus large number, it's small. Transmission probability is small. Notice if the energy is much less than V naught, again, kappa is large, very small transition probability. Also notice if W is large, very wide barrier, small transition probability. Okay. But if we've got a narrow barrier, and V naught's not too high, and if we've got a small mass like an electron might have, the transmission probability becomes non-negligible. And it can happen. So this is a very curious term. A small particle, even though it has less kinetic energy than the barrier height, can in principle travel through. And this has been observed time and again. Classically, we don't observe it because classical things are too massive for this to be observable. But really tiny things can. And this is the basis for lots of interesting technology, like scanning electron tunneling microscopy, which is for mapping out the surfaces of things at a very small scale, uses that. I'd love to tell you about it. The concept of kinetic isotope effects, which either you've heard of or you haven't, I don't have time to explain them, but they're based on protons tunneling through a region of space they shouldn't be able to get through classically. And that can tell us about the mechanisms of chemical reactions. So this turns out to be very important. Okay. I need to leave you though with the last picture. And let's think about this tunneling region. What is going on? And let's draw our baseline right up here. Let's say that's where energy is. And let's plot the real part of psi. Our wave function is complex, but it has a real part and an imaginary part. For a picture, it's hard to draw them both. I'm just going to draw the real part, okay? And imagine what's happening. Well, we know that out here, we have a complex exponential, and the real part oscillates sinusoidally. Remember, e to the ix equals cosine x plus I sine x. So this is like a cosine function. Out here, we're also going to oscillate, okay, because the potential energy is zero. What happens in here? We have two parts to this wave. Let's focus on this. This is a decaying exponential, entirely real, but the bigger this exponent, the smaller it gets. So what happens in this region is that function decays, and it decays very quickly towards zero, but it never gets to zero. So what happens is your particle encounters the barrier, the wave function decays, but unlike classical physics, where the wave function would immediately be zero, and we wouldn't call it a wave function, but you'd immediately have nothing. Quantum mechanically, a friend of mine told me, and he's now a PChem prof elsewhere, he recollected his teacher's comment that in quantum mechanics, the rough edges, they get smoothed out. And that's actually a nice image to keep. So you want to stop, you decay to zero. Then, so in the tunneling region, remember that you have a decaying wave function. So within the wave, outside of the tunneling region, the wave function is oscillatory. Inside the tunneling region, decays. The bigger W is, the bigger V naught is compared to E, and the bigger the mass, the faster that decay. But if you've got a really fast electron, if you got an electron, small mass, and the barrier is not too wide, it might travel through. Now, if you really observe it, you might notice, this is a footnote, okay? If you really observe it, you might notice psi 2 has a second part. It's not decaying, it's getting bigger. If I do that second part, it's getting bigger. The opposite of what I said. In fact, it goes to zero, I mean to infinity. It gets infinite, it just keeps going up. I can't deal with that very well visually, right? But what this implies, by the way, because that's non-physical, it doesn't keep getting, it just doesn't make much sense. So what this implies is I'll tell you that the coefficient of the increasing part when you solve the equations is much bigger than the coefficient of the decreasing part. In fact, if your barrier gets infinitely wide, C goes to zero. I said it backwards. C is much less than V. So you're going to find a worksheet that takes you through some of these ideas, and there's also a problem that's related on the homework. In deference to Steve, what time is it? I really wanted to look at the. We're okay. Okay. I can take a deep breath, and I can say any more questions on this. Yes.
So why does that happen though?
Well, that's just a feature of mathematics. The larger x gets, the bigger this exponential gets. That's a feature of mathematics. Sorry?
It doesn't have a physical reason.
No, there's no physical reason. Right. But it turns out, because that's the case, that C, when you solve the whole set of equations, C becomes unimportant. So generally, when we're thinking about tunneling visually, we don't even bother drawing that in. It's just the important part of side 2, the decaying part. Yes?
And is it related to like ultraviolet spectroscopy?
Ultraviolet.
Spectroscopy, so kind of the wave pools that have to do a medium.
Well, yeah, so it is true. This behavior we're talking about doesn't comport with classical ideas. Right? But again, if you ask yourself, where does it come from intuitively? It comes from the wave nature of the waveable. So sound can travel through that wall, and it's hard to say that sound has a lot of energy enough to get through that thing. That takes a lot of hard thing to do, but a medium can allow a wave to pass through the medium, and that's kind of the way to think about this. Wave-particle duality. So maybe I'll bring up a couple more clear examples of where this is important. I only have time to say it verbally: scanning, electron tunneling, microscopy, and the kinetic isotope effect. But there are lots of places where it has direct impact technologically. And what's to remember? If you do the same thing for an energy higher than V0, classically you're going to be transmitted, right? Guess what happens quantum mechanically? You might be reflected. But it's not so, I mean, that's not really the, so we're going to go to this. So we're going to go to this. Both of these things, we're going to respect Steve, and we're going to show you a picture. And Steve's dying here. I know he's dying. But I'm going to show you the picture. Okay. You're going to find this picture in your text. It's a complicated picture. Just look at this for now. It has transition probability as a function of the incident energy, or actually E divided by V0. Because these are all numbers less than 1 here, we're talking about where the energy is less than the barrier height. Now these other numbers, 2, 4, and 10, account for different scenarios, like how wide is the barrier compared to how, and what's the mass. Read the details. But so for certain widths and masses, this is what the transmission probability looks like. Notice even when the energy is equal to the barrier height, the transmission probability only gets to 0.5. For even wider barriers or more massive particles, it's even less likely to go through. It's a lot there. This is the funky thing. What happens when E is greater than V0? You never quite reach 1. That's because of the non-classical reflection I talked about. And the oscillating part, oh, I'd love to tell you that story. That's too long a story. If you're really curious, see me some other time. Okay. Let's go to this worksheet. So, I'm going to stop talking for a second. So this goes back to last class. We looked at the 2D harmonic, the 2D particle in a box. This goes to 3D. And it turns out that the energies, because we're in 3D, there are 3 quantum numbers. And if the box is cubic, so each side is the same, we call it L, then this is the total energy. And I asked you to think about the energy. So first I said, what's the energy of the 1, 1, 1 state? N1 is 1, N2 is 1, N3 is 1. And just give your answers in multiples of h squared over 8ml squared. Let's keep the math simple. So in this case, we have 1 squared plus 1 squared plus 1 squared times h bar squared over 8ml squared. Let's just call this 1 plus 1 plus 1 is 3. The units are this stuff. So, well, I guess here I wrote out the h squared over 8ml squared. So, is this level degenerate or non-degenerate, and why? It's non-degenerate because there's no other state, no other set of those 3 quantum numbers that can give you the same number 3. What's the energy of the 1, 1, 2 state? Well, it's it's 1 squared plus 2 squared plus 1 squared, so it's 1 plus 4 plus 1, or 1 plus 1 plus 4. So that's 6 in units of h squared over 8ml squared. And the energy, notice that 1, 1, 2, 1, 2, 1, and 2, 1, 1 all give the same energy. They are different states because position is a fixed thing. You know, what is the x coordinate, what is the y coordinate, what is the z coordinate? Those are clear. So n equals 1, n1 equals 1 is not the same as n2 equals 1. Right? So those are 3 different states. So we say the degeneracy is 3. 1 energy level, 3 different states. Now if we look at E equals 14, blah, 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 you have to ask yourself, the question is, what states will have this energy? You just have to sort of trial and error. But you would find that 3, 2, and 1, 3 squared plus 2 squared plus 1 squared is 14. But you have to, if you ask yourself, what are all the possible states that will have that value of energy? You have to permute these numbers all the way as possible. 1, 2, 3, 1, 3, 2, 2, 1, 3, 2, 3, 1, 3, 1, 2, 3, 2, 1. Degeneracy is 6. So, is it a hard concept? Not really. It's important. It brings home the distinction between energy level and state. Why is degeneracy important? You don't understand that yet, probably. But it will be, so just pay attention. Oh, this last one. I know. If you count it, if you ask yourself, what is this last one? How many states are there in 3D with an energy less than or equal to 14? And you find out, if you count them all up, there are 17 states. What if you thought about 1D? Same energy, 14. How many states are there? It turns out if you count them up, didn't I put that? Oh, in 1D there are only 3 states. N equals 1, N equals 2, N equals 3. Because if N equals 4, the energy is 4 squared, which is 16. So we talked about something called the density of states. How many states are there within a given region of energy? And we find that the density of states increases dramatically as you increase the dimensionality. So that's kind of interesting. Can you think of other examples of degeneracy? I gave you one at the very top. You can go back and read it from biology. We will find, you probably remember when you draw energy level diagrams, you say, okay, s orbital, and then you say, okay, p orbital, 1, 2, 3, because there's 3 p orbitals, and you draw them at the same level. That's because the p orbitals all have the same energy, px, py, pz, at least as long as they're unfilled. So the px, py, and pz are degenerate. So this begins maybe to convey why this topic is going to be important. Thank you, Steve. Anyway, we're done for the day. I'll just remind you, there's the worksheet, there is the problem set, there's the study hall. today. Remember the quiz? You don't have special studying to do for the quiz. You might look over your notes, as long as you've been studying so far. But it's an opportunity to get ready for the exam, which is to follow it. Have a good weekend and enjoy this word as well.